through a number of events from the history of mathematics, and initially a whole range of different things, just pointing out, really giving an origin of the whole length of time that this has been a cultural history of stretching way, way back. And then we're going to have a little bit of time to discuss the possible advantages of using the history of mathematics in teaching mathematics and adult numeracy rather than it being a subject of its own. Right, if we move on. Thanks. Right, so we begin with where on earth measuring the 12-hour day. And as we see that this goes back to 3,500 years, give or take probably 500 years, into ancient Egypt, the whole idea of dividing it into 12 hours. Okay, next. So the ancient Egyptians, in fact, had a measuring system of measuring the stars really passing down past the horizon. And in a way, it was the measurement of those that initially gave a division of it into 12 throughout the night, and that they could measure by shadow clock during the day and matched it with 12 there. And so they were not necessarily all the same length when it all first started in that way, but we go back to a 12-hour day and a 12-hour night back to 1500 BCE. Moving on, we now move to something completely different. The Lo Shu, the Chinese magic squares, which really is difficult to know where that originally began from. It's thought that it's sort of at least somewhere around 3,000 years ago, 1000 BCE. And we have these images. The one on the left is taken from a form of dot numbers that the old Chinese mathematics had used at one time, and a modern version with our familiar numerals next to it. And of course, if you're in this idea that you have a set of numbers where every line, vertical, horizontal, and diagonal, all add to the same number, with this version, I suppose the starting version of it be adding to 15 in every direction. So this was if you like, a beginning of a playing with numbers, but going back a very, very long time. So we move on to one of the most key parts of what's considered in certainly teaching mathematics for many, many, many hundreds of years, of it being based within geometry, looking back into the early universities, certainly of Europe, was that the mathematics was seen as geometry, was even the name given to the professors of geometry. And the definition there of Euclid producing his definitions and producing his foundation of geometry. And here we've got an example of really where the history itself takes us through many stages, that as we saw that Euclid himself was at 300 BCE. But here on the left, you have a version of Euclid that was in the first printed version in Europe, and another version on the right, which was a particular version produced, as it says, in the middle of the 19th century, where a whole set of what is equal is given out through using numbers rather than labeling the sides. And this Burns Euclid is a beautiful book if you get the chance to see it. But here we see the transition of that basic of geometry going through those stages, and of course now it moves into other things that can be produced, of course, with our new technology now as well. We move on. Another founding part of the mathematics that is used now is, of course, the use of calculus, which was, in fact, one speaks about it as an invention. It moved the mathematics on, and as quite often happened in mathematics, there was two people working on it, Isaac Newton in England and Leibniz in Germany, and it became one of those cases which can sometimes be a little tedious, but it became one of those cases where there was a lot of argument about who did one of these people steal it from the others, and it's generally accepted that they were independent, but working on calculus, but produced two different versions. Move on. So Newton brought in this naming of fluxions in his description of it, which was not in Leibniz, and although it became that, in fact, how it's spoken about now and the symbols that are used in calculus now is very much, in fact, what Leibniz produced in his version. But this is one of those cases, and it's whether it seems a long time ago or not, but it's back in the middle of the 17th century that this essential part of all of mathematics that is done now was developed by these two mathematicians in that time. So we move across and jump to the 19th century, where there was beginnings of modern mathematics, which goes into many places and much harder to look at succinctly as a sort of a history, but this form of non-Euclidean geometry began to evolve in the 19th century. And as a reminder of what it is, move on, is that it's the geometry basically on a non-flat surface, and here showing a version of it put onto the globe, where in fact the standard facts, such as the angles of a triangle adding to 180 degrees, is no longer the case. And so across the whole surface of the globe, you get a different geometry, whereas measuring shorter parts of the on surface, the curvature doesn't affect it, as in the little minor drawing in the illustration. But this was the beginning of a whole development of major mathematics, and the beginning of maybe people actually being considered mathematicians, probably around this time into the 19th century. Move on. Taking a different version, we move into what in fact is seen as one of the earliest forms of developing statistical diagrams, where we have Florence Nightingale producing what were called at that time polar area diagrams, in a way rather similar idea to a pie chart, middle of the 19th century. And move on. And it's said that really from her producing this and working through the statistics of the time, she saved far more than in the nursing. And as you see here, those very large areas of the bluish grey were identifying where people were dying from contagious diseases. And so this is an important part of that development of in fact statistics from that middle of the 19th century by Florence Nightingale. And looking at some other forms of linking into science, the metric system that is universal now interestingly came about during and was a specific decision being done by the scientists and mathematicians at the time of the French Revolution in France, that a whole new system of measurement was designed. And this, in fact, that there still remains in one place in Paris a standardized meter that at that time were put up. This kind of rather nice diagram here shows that the system covered all the forms of lengths and area and volume and various measures of capacity. They did, in fact, also decimalize the calendar, but that is not one that carried on, whereas the metric system they invented has become sort of virtually, very, well, nearly very universal, not quite everywhere, but is commonly used. Next. And carrying that further forward now into the 20th century, and agreement within science to needing something that, in fact, in science, if not in any other measurement, that a whole system of units was important, that there was an international agreement of having the SI units agreed really universally. And these are showing on the next slide, that the base units are given there of the second meter. Surprisingly, the kilogram and not the gram was chosen, and the ampere, Kelvin, mole, and candela. So these became the defining numbers with certain mathematical constants, scientific constants, helping to establish the precise nature of those scientific measures. Something that obviously continues today to be very, very important. And my final item for this first part of the of this is, I thought I would include fractals, which really were very, very much linked to the development of computers as they began towards the end of the last century. And there were these sets were developed, and there was an early version with not such powerful ones by two scientists, Brooks and Natelski, and then in 1982 the more famous Mandelbrot set was popularized and produced in Mandelbrot's book of The Fractal Geometry of Nature. And importantly, what, apart from producing the mathematics behind the whole setting of the fractals that it produced, was the argument that this enabled, through mathematics, the science to analyze irregular phenomena, which had always been difficult to do in more sort of classical approaches in physics, and the mathematics applied to that. So that is my end of my first part of the items out of a whole wide range of I think mathematically important aspects, going back, as I say, going right back in time for 4,000 years. And these are, to my mind, things that help us look at the importance of mathematics in many, many, many different aspects. And I think it's, I for many years was teaching adult numeracy, that I saw it as a way that helped people get into it who are not very comfortable with the mathematics in itself. And so what I'd like to present to you and suggest that we discuss are some reasons that have been suggested that I think are important to why it's useful, and different parts of mathematics, obviously picking just one or two topics and not as many as I have suggested here, of the reasons of why they might help in an adult numeracy classroom. I think we're going to break into 2 or 3 groups, are we, Judy?
Yeah, so I'll just mention something here. I'm going to send a link in the chat. If everyone could open that link, it'll give you access to the slides. If you click on this conference picture, it leads to the slides. So if you would like to refer back to some of the topics that David has introduced. And just down here are the part 1 instructions from the slides. And if you could spend about 5 to, I don't know, 8 minutes or so chatting about how these prompts, and if you have a response, you can just add a comment and click that there so we can see some of the ideas coming out of the groups. So hopefully everyone has that link, because once you enter the breakout room, you will not have access to it. So we'll just try it out and we'll come back in about 5 minutes or so. And then David will continue with some more parts to the history of mathematics.